Continuing our 1.1 lesson, we started at the last video talking about this idea of continuity at a point. So this is one of the first big ideas of our chapter. A function is continuous at a point, x equals c, if the left-hand limit equals the function value equals the right-hand limit. Okay, the road in, the road out, and the bridge all have to be connected. So we have this, using this idea here of continuity, we're trying to determine whether this graph is continuous at the following points. And we have to justify that. You're going to see that on all kinds of worksheets, on all kinds of quizzes, tests, the AP exam. Okay, so let's try plugging it in. We need the left-hand limit. Remember, left-hand limit has to equal the function value, has to equal the right-hand limit in order for it to be continuous at a point. So if we take h and plug in 2, okay, at the top we're going to get 0, and at the bottom we are also going to get 0. 0 over 0, it's undefined, so we know that there's a hole there. So we would say h of x is not continuous at x equals 2, since h of 2 is undefined. Okay, it's that simple. H of 0, let's try plugging that in. Make this a little skinnier. All right, h of 0. We get 0 on the top, not a good start from last time, right? And we get negative 20 on the bottom, so we have 0. Okay, so let's try the limit as x approaches 0 from the left of h of x. Okay, this would help if we factored out this h of x function. So we could take an x, then you get x squared minus 4, which turns into x minus 2, x plus 2. And then it looks like we're going to have, what would that be, x plus 10, x minus 2. All right, so if we plug in 0 from the left or the right, it doesn't matter. There's no problem at 0. We're still going to get 0. The limit as x approaches 0 from the right of h of x, 0. So since the limit as x approaches 0 from both sides equals h of 0, h of x is continuous at x equals 0. All right, and we have one more here. Okay, so let's plug in h of negative 10. I can already tell you that's going to be undefined because of this bottom term. H of negative 10, undefined. So there we go, h of x is not continuous at x equals negative 10, since h of negative 10 is not defined. Okay, and it's really good to practice justifying this, to practice the wording, because a lot of people get caught up on that. All right. Let's clear that out. There we go. So if the limit as x approaches c exists, but f of c is undefined, or the limit doesn't equal the function value, then there is a hole at that value. All right, so we're going to look at that. Piecewise functions give really good examples. Okay, it's kind of like this bridge down here. They started on this side, and it just didn't line up. Okay, so it's not going to be continuous there. So algebraically determine the following. Well, let's see, f of 2. This is for x less than 2. This is for x greater than 2, but we don't have anywhere to plug in when x is 2. So we have that undefined. There's going to be a hole there, at least, or could possibly be a jump. Okay, for b, if we want to find the limit as x approaches 2 from the left, you got to know what part to plug it into. So the left side of 2 is going to be everything less than that. So we're going to be plugging it into x squared, the x squared part. Let me erase that. And so we get 4. The limit as x approaches 2 from the right side, this time we're going to be plugging it into this, we get 3. So then the limit as x approaches 2 from the left and the right of f of x does not exist because 3 is not equal to 4. Okay, the left-hand limit didn't meet the right-hand limit, so the limit does not exist. So when we talk about the continuity at x equals 2, we would say that f of x is not continuous at x equals 2. And there's a lot of reasons. Since f of x, or since f of 2 is not defined, okay, that's one thing we could say. Since the limit as x approaches 2 of f of x does not exist, okay, the limit doesn't equal the function value, any of those reasons would be fine. So here, again, this is formalized. If the left-hand limit doesn't equal the right-hand limit, then there is a jump discontinuity there. So we're going to discuss this function and figure out where it is continuous. Okay, x plus 2, that's just a linear graph. That's not going to be discontinuous. X squared over 2, that's a parabola that's slightly wider. And y equals 2 is just a horizontal function. So the functions themselves are all continuous. So then the only places where they might not be continuous would be where we've switched to different values, like -2 or +2. So those are the places we have to check. All right, so let's start with -2. F of -2. Well, we're going to plug that in here because that's when x equals -2. -2 squared is 4, divided by 2 is 2. Okay, now let's check the limit as x approaches -2 from the left. So that would be this part of the function, x plus 2. Looks like we get 0. Okay, the limit as x approaches -2 from the right. This would be this part. We already know that's 2. So f of x is not continuous at x equals -2, since f of -2 is not equal to the limit as x approaches -2. All right, the only other place, let's check f of 2 this time. F of 2 equal, and again, we're going to plug it into here. We're going to get 2. Limit as x approaches 2, if we go from the left, we get x squared over 2. That's the part we're plugging it into. We know that's 2. Limit as x approaches 2 from the right. Well, this is the right-hand function, so that's just 2. So f of x is continuous at x equals 2, since f of 2 equals the limit of f of x as x approaches 2. Okay, this one had the smooth road in, bridge, and road out. Whereas over here, we were at 0, and then we went up to 2. So we had this jump discontinuity there. All right, so sometimes you're going to get variables instead of numbers, and you have to figure out what they are. Okay, this is a very common type of problem, and I think this will be the last one that we'll do for today. So find the values of a and b such that f of x is continuous at x equals, I'm going to change this to be x equals -1. X equals 1, it won't be that exciting because all of these say -1. Okay, so there's a small mistake in that. No big deal. All right, so we have, if we want it to be continuous, we have to figure out what's f of -1. That is 4. Okay, we need to take the limit as x approaches -1 from the left, and the left side would be this part of the function. So if you plug in -1 for x, we're going to get a minus b. Okay, then we have the right-hand side. X approaches -1 from the right. So that would be this part. plug in -1 for x, so we get -2a plus b. If we want it to be continuous, we need the left-hand limit and the right-hand limit to be equal. And we also need, okay, the function value to be equal to those. So we need a minus b. That has to be equal to 4. The left-hand limit has to be equal to the function value. The right-hand limit also has to be equal to the function value. So now we have a simple system of equations here. So you should know a couple different ways to do this. You could do substitution. I'm going to choose elimination because I could just add these straight on. So a minus 2a is -a. Negative b plus b, they're gone. 4 plus 4 is 8. So that means a equals 8. Okay, substituting that back in. Oh, a equals -8. Ooh, that could have been a big mistake. Okay, substituting it back in here. -8 minus b equals 4. So solving that, we end up with b equals 12. So all we had to do was find the values of a and b such that f of x is continuous there. And it is, if you plug them in, you can find that out. We'll almost miss that one again. A equals -8, b equals -12, and that's the end of our video.